everyone, and thanks for watching Edupedia World Videos. In this video we begin our study of the refraction of light, and we begin of course with refraction at a planar surface. Now just like for mirrors, we will not be deriving the formula Snell's law for refraction. We've already done that using Huygens principle. Now all we are going to be doing is using that principle to figure out some results. So let's say this is mu1, this is mu2. Light goes from an object in mu1, instead at an angle I, it is refracted at an angle r, it goes to mu2. So Snell's law, which we've already derived, basically states that mu1 sine I is equal to mu2 sine r. Right. Now it has one interesting effect. It looks to us, when we look at an object coming from another medium, that it is at a different height from what it actually is. So what happens is, now in this case we just assume, of course, since r is greater than I, we've assumed that mu1 is greater than mu2. Right. So let's assume for a second that mu2 is air. So we'll just take mu2 is equal to 1 and mu1 is maybe water or glass. Then an object that is placed inside water or glass will actually look to us to be of a different depth than it actually is. So if we have our eyes over here and we are looking from here, or actually our eyes should be here, then this ray coming into our eye, it looked to us as though it came from this point. Right, so instead of the object being here, the image of the object will look to us to come from this point. Let's say this depth of the object in the water is h. Our goal is to find this new h dash in terms of h. So that's easy enough. Let's call this length L. This total is r. Sorry, this isn't r. This is I, so this is I, and since this is r, this is r. Right. So what is h? We can tell that L by h is equal to tan I, which I can write just as equal to sin I, because we're assuming that I and r are relatively small. Right. Similarly, we can assume L by h dash is equal to tan r, or we can just write it as sin r. And once we divide these two, what we'll get is sin I by sin r is equal to h dash by h. What is sin I by sin r? It is equal to 1 by mu1. We'll just write it as 1 by mu right now. So h dash by h is equal to 1 by mu. And it tells us that h dash is equal to h by mu. So this is the apparent height. H dash is the apparent height of something in water, and h is the actual height. We see that the apparent height is reduced from the actual height by a factor of mu. This is one of the reasons why you've probably heard when you go near a swimming pool that the water actually looks shallower than it is. Because let's say this is the bottom of the water surface, bottom of the pool, rays coming from the bottom will be refracted, and it will seem to us that the water has only a height of 2 meters when actually it might have a height of 5 meters. Right. So this is the formula you need to remember. I generally don't remember it. It's easy enough to derive very clearly from here. But the apparent depth is the actual depth divided by mu. It also tells us another interesting thing, that if this height h is the total height in the medium, then what will this shift be? The shift, or we generally call it as delta t, the shift, it will be h minus h dash, or h minus h by mu, or h into 1 minus 1 by mu. We'll just write h as t for a second because t is the thickness of this medium. So the other important result we get is delta t is equal to t times 1 minus 1 by mu. This is the result which tells us the shift, or the apparent shift in the object. Whenever we look at an object, and this, by the way, you can, instead of mu, you can put it as mu21 or mu12 when it's with respect to two mediums. In this we've taken one as air, but if we took water and glass, then mu would be the ratio of the refractive index of glass and water. Right. So if we take an object coming from a medium of higher refractive index going into lower, then we see that the apparent depth is actually smaller than the actual depth, and it seems to us that the object is shifted from its original point by an amount t times 1 minus 1 by mu, where t is this thickness of the medium over the object. This also helps us in figure out, for example, if we have some written words on a page and if we put a glass block on it, then words will go from here like this, go like this, and they'll seem to us to be here. So that's why whenever we put a glass block on some written words on a piece of paper, then it seems to us that they are raised, because the apparent height changes because there will be a shift, and in this case t will be the thickness of this glass slab. So this is refraction at plane surfaces. It is simple enough. Let us move on now to refraction at spherical surfaces. Now here again, students sometimes get confused between refraction at spherical surfaces and refraction due to a lens. They might use the lens formula for refraction at spherical surfaces, which would be very wrong. So let's see what refraction at spherical surface means. It just means we have a spherical surface which has a refractive index mu. Let's take this to be 1. Right, that's it. That means if we take an object going from this point and incident rays going from here to here, all this material within this region, all of this is of refractive index mu. This might actually be a whole ball, right, and all of this refractive index mu. I'm just drawing that to illustrate the difference between this and a lens. In a lens, this would be the object, and a lens is like this. A lens is composed of two refracting surfaces, but only this middle area is mu. This is air, this is air, this is air, all of this is air, only this small area is mu. It goes from air to glass and back to air. Right now we are only considering air to glass. And some of the intelligent ones of you might have realized that refraction through a lens will just be air to glass and then another refraction from glass to air. Right, so for a thin lens, you'll have to use refraction at spherical surfaces at two separate points, and that's how we'll actually be able to derive the lens formula. But when you have just a single spherical surface, then make sure you never ever use the lens formula, you use the standard refraction at spherical surfaces formula. Right, so let's look at that formula now and let's try to derive it. This is the spherical surface we have. Refractive index mu, this is 1. By the way, whenever I take mu and 1, you can take it to be mu1 and mu2, and mu1 by mu2 you can substitute that for mu, right? Because relative refractive index is the refractive index of one divided by the refractive index of the other. In this case, let's just make it slightly more complicated so that we'll do the more general case. So in this case, let's take this to be mu1 and let's take this to be mu2. But generally mu2 will be some material and mu1 will be air, right? Now let's mark some parameters first. Let's say this is the pole. Let's say this is the center of curvature. Again, center of curvature will be the center of the sphere from which the spherical surface is carved out, or of which the spherical surface is a part. Let's say this is O, the position of the object. So one ray goes here and it will just straight away go here, because now this ray is perpendicular to the surface here. And if you take a plane surface and a ray goes perpendicular to the surface, that is parallel to the normal, it is not deviated at all. Psi I and sin r are both 0. Right. Let's take another ray which goes like this and is refracted at the spherical surface and comes back, let's say, like this after being refracted. Right, so this is I. We'll just extend this a little bit. This line going from the center is actually the normal to this surface, and we've seen that in spherical mirrors as well. The point from the center to the edge of a sphere is perpendicular to the tangent, or it is the normal. From that we can tell that this angle is the angle of incidence, this angle is the angle of reflection. So the first equation we have is mu1 sin I is equal to mu2 sin r. Now let's write down some other angles. Let's say this is alpha, this is beta, this is gamma. So the first equation we can get is beta is equal to r plus gamma. Right, if you look at this triangle, beta is an exterior angle to r and gamma. Similarly, we can also write I is equal to alpha plus beta, because if you take, let's call this A, if you take triangle OAC, then I is an exterior angle to alpha plus beta. Alpha plus beta plus this angle is 180 and this plus I is 180. So these two equations you get. Also mu1 sin I is equal to mu2 sin R. We can write it as mu1 I is equal to mu2 R. And that's only because again we are assuming rays to be paraxial, and if rays are paraxial then I and R both are quite small, and we can use the limit that sin I is equal to I when I is very very small. Right. From this we can get the result mu1 times alpha plus beta is equal to mu2 times beta minus gamma, or mu1 alpha plus mu2 beta is equal to mu2 gamma is equal to mu2 minus mu1 beta. Right. So this is the result we got. You can see that the structure is beginning to resemble the refraction at spherical surfaces formula. Now we'll just use again paraxial approximations. Alpha can be written as AP by PO, beta can be written as AP by PC, and gamma can be written as AP, but this is I, sorry, by PI. Another important thing, take care of the signs now. What is U? U is not equal to OP, U is equal to minus OP because U is negative. What is V? V is actually equal to PI. V is not equal to minus PI because this is on the right side. If the length of PI is 5 meters, then the position of the image is plus 5 meters because it's on the right side. Right. What is R? R is equal to CP. Again, there is no minus because it's on the right side. If instead of this, the spherical surface would have been curved the other way, then the center of curvature would have been towards the left, and R would have been negative. But right now we know R is equal to CP. From that we get the result, only negative is OP. OP will be for alpha, so alpha will be negative. So we get mu2 by V minus mu1 by U is equal to mu2 minus mu1 by R, which is the standard formula for refraction at spherical surfaces. This is the way I remember. Mu2 is for V because V is towards the right and mu2 is the right side medium, right? So mu2 by V minus mu1 by U is equal to mu2 minus mu1 by R. Now we'll try to figure out the magnification, and again, just like in the case for mirrors, magnification does not mean anything for a point object, so we'll have to consider an extended object to calculate magnification. So again, let's say this is our surface. Let's say this is mu2, this is mu1, and this is an object kept like this, an extended object. So the bottom will go like this, it will just pass through undeviated, and we actually know of another ray that will pass through undeviated, and I'm sure you've used this concept when the image of the lens was formed due to image tracing instead of using the formula. So a ray which is projected towards the center of curvature will pass through undeviated because the center of curvature will be a normal to this point, and the ray going through the normal will just go undeviated. So if this is true, a ray is going undeviated, then this point has to be the center of curvature, right? And in that case the image will be something like this. This point will have an image here, the upper point will have an image here, so this object will have an image here, right? Now let's label some things A, B, P, C, D, E. So what is the magnification? The magnification will not be DE by AB, it will be minus DE by AB, because DE is positive, however the height of the image is negative because it's inverted. So minus DE by AB, right? Now since these two angles are the same, this is 90 degrees, these two triangles are similar, so we can write DE by AB as DC by CA. So this is equal to minus DC by CA. Now we can write this as negative of DC will be DP minus CP. What is DP? DP is V minus what is CP is R divided by, now CA will be the tricky one. CA is equal to AP plus PC. What is AP? AP is minus U. U is negative but AP is positive, right? So AP is minus U. What is PC? PC is R. So plus R. Right. So what will this give us? That gives us minus U plus R. Or if I wanted to simplify it a little bit further, what it would give me is this would be R minus V by r minus u. Now I'm not going to simplify it a little bit further, it gets a little bit complicated, but using the formula mu2 by v minus mu1 by u is equal to minus mu1 by r, you can eliminate r and you can just simplify this. It's not that hard, but it's lengthy, and it will come out to be m is equal to mu1v by mu2u. You have to prove that mu1v by mu2u is equal to this term, and that can be easily proved using the spherical refraction formula. Mu2 by v minus mu1 by u is equal to mu2 minus mu1 by r. So this is the final formula for magnification, mu1v by mu2u. In this case, we see that u is negative but v is positive, so the magnification automatically will come out to be negative. Right, so this is including the sign. Now let's move on to the next case, which would be lenses. Now a lens is nothing but two spherical surfaces kept very close together. And going from a refraction at spherical surface to a lens seems a little bit complicated because the refraction at spherical surface formula is not as simple as the lens or the mirror formula, but it actually turns out to be quite easy, even mathematically. So all I need to do is I'll talk about the different types of lenses in a minute. This is the standard convex lens. Right now we'll just assume this one lens. Let's say this is 1, let's say this is mu, and let's say this is 1. Now another assumption we'll make along with paraxial is that this is a thin lens. Thick lenses are not in your course at all, you'll do them once you go to college, and right now every lens we'll assume will be a thin lens, and the thin lens basically means that this thickness is very small compared to u, v or r. Right. Now let's say we've kept an object here, O. Right. It goes through the first surface, and because of the first surface, it has an image that is created here. Let's call this O dash. Now the image O dash is created by this surface. Now O dash becomes the object for this other surface, and let's say this object O dash, when refracted through this, has an image somewhere here, I. Right. So in that case, we know that the net image of O is I after two refractions. Again, actually I would prefer it to do just mu1, mu2 and mu1. So it will be the more general case, and you can just put mu1 is equal to 1 if you were taking a system that is done in air. But if we take mu1, mu2 and mu1, then we might even actually be able to apply this formula for a lens system in which the experiment is done underwater. Right. So the equations will be easy enough. The first equation will be for refraction at this surface. Right, and let's say this surface has a radius of curvature r1 and this surface has a radius of curvature r2, and we are assuming the sign as well. So r1 will be positive because it's towards the right, r2 will be negative because it's towards the left. For the first refraction, what we'll get is mu2 by v minus mu1 by u is equal to mu2 by minus mu1 by r. However, this v, we just call this as v1. This v is not the position of this actual image, this v is the position of this image. There's no specific reason I've drawn this image to the left and this to the right. We are assuming a completely general case. So this is 1. Now if this v, this is v, or with the appropriate sign, then if we wanted to make it the object distance for this other lens, then we would have to add this thickness as well. Right, because this is the first pole, this is the second pole. And this is where the thin lens approximation comes in. We'll assume that this distance is so small compared to v that we'll just take all the distances measured from the center. So the pole in this case would be the center, everything would be measured from the center. Right. So the second equation would be mu1 by v, because now it's going into mu1, minus mu2 by u. Now u would actually be v1 plus t, but we'll just take it to be v1. Because we are assuming it's a thin lens, and that is equal to mu1 minus mu2 by r2. This is r1, sorry. Now keep in mind r1 is positive, r2 is negative, but we are assuming this with the sign. Now it's easy enough, we just add these two equations, mu2 by v1 will cancel. And this is where a thin lens is very useful. Imagine if we did this to be v1 plus t, where t was the thickness. If t is the thickness of the lens, we put v1 plus t here, then these two would not cancel, and it actually would end up being very complicated. In fact, the theory of thick lenses is quite complicated. That's why you don't do it in your classes. But if we assumed it's a thin lens, then these two cancel very easily, and what we are left with is mu1 by v minus mu1 by u is equal to mu2 by mu1, mu2 minus mu1 times 1 by r1 minus 1 by r2, because this is mu1 minus mu2 divided by mu1, and you get a standard result which you've probably seen before. 1 by v minus 1 by u is equal to mu2 by mu1 minus 1 by r1 minus 1 by r2. Right. Now, this is also basically called the lens maker's formula, because it tells us how to make a lens, because we know the actual formula for a lens is 1 by v minus 1 by u is equal to 1 by f. Right. So what is 1 by f? 1 by f is equal to mu2 by mu1 minus 1, or if you're doing it in air, mu minus 1 into 1 by r1 minus 1 by r2. This is called the lens maker's formula because it tells people who used to make lenses, if you want to make a lens of focal length, let's say 20 centimeters, and these are the refractive indices, then this is the combination of spherical surfaces radius you'll need to actually make this focal length. And once we made this focal length, then we don't need to worry about this upper equation. We can just look at this lower equation. 1 by v minus 1 by u is equal to 1 by f. The last step that is left, you guessed it, magnification for a lens. Now again, for magnification, we'll need an extended object. That's easy enough again if we just take a lens like this. Now a property of the lens is that a ray that passes through the pole goes away undeviated, because this is almost parallel to this, because these are close. So we'll just take these two to be normal, and then one ray will probably go like this, the other ray will probably go like this, pass through the center. If this is the image, then it's again easy enough. A, B, P, C, D. We know that the magnification will be minus CD by AB, right? But we know that U is equal to minus BP and V is equal to positive CP. And because these two triangles are similar, what we can do is CD by AB can be written as CP by BP. But CP is V, right? So is equal to minus V by BP is minus U, is equal to V by U. So for a lens, the magnification is V by U. For a mirror, remember it was minus V by U. Right. So this is how we derive the lens formula. Now let's look at a few concepts related to lenses, which I talked about for mirrors, such as the first focal length and the second focal length, which tend up to be a little bit more complicated for lenses. Now, what did we say these two focuses were? The first focus was U when V is equal to infinity. The second focus was V when U is equal to infinity. Let's look at our equation. 1 by V minus 1 by U is equal to 1 by F. We can see it directly that these two will have the opposite sign, because if we take this to be 0, then 1 by U is equal to minus 1 by F. If we take this to be 0, 1 by V is equal to 1 by F. Right. And let's see how that relates to convex and concave lenses. This, by the way, is a concave lens. It's sometimes called a biconcave lens because both sides are concave, but for short it's called concave lens. Then you have convex lenses, which would be something like this. And then you even have combinations, concavo-convex and convexo-concave lenses, which are not in your course, but they might be like this, where one surface will be convex and the other surface is concave. Right. But right now we'll just focus on the basic one, convex and concave lenses. So for a convex lens, the second focus, remember the second focus is the more important focus. What is this focus? V when U is infinity, V is equal to F. When V is equal to infinity, U is equal to minus F. So 1 by F is 1 by V. The second focus is the more important one, and that is the focal length which we use in the formula. Right. So V when U is equal to infinity. U is equal to infinity means rays come parallelly. When they come parallelly, they'll meet at the focus. Right. So for a concave lens, then we'll do convex as well. The first focal length and the second focal length. The second focal length is positive. Right, because this is positive. However, what is the first focal length? What is U when V is equal to infinity? Now V is equal to infinity means the final images will be at infinity like this. Right. Now if the final images are at infinity like this, then the object has to be here. Right, an object placed at the focus will give parallel rays. right? So this is the first focal length, and we can see that it's negative. For mirror, first and second focal length were the same. For lens, they are an opposite, right? For lenses, the first focal length is where the object should be kept so that the images come out parallel, and the second focal length is where do rays that come parallel actually meet, right? So this is the second focal length where parallel rays meet. This is the first focal length where if we keep an object here, they'll move out parallel. And the same thing, let's see for convex lenses. So for convex lenses, it will be like this. By the way, concave lenses are called converging because they converge parallel rays at a particular point. Convex lenses are called diverging. Now, second focus is the easy one. It is V when U is infinity. U is infinity means the rays come parallel. If this is the principal axis and rays come parallel, since it's a diverging lens, rays will go like this. But they will appear to diverge from this point. That means V will appear to be this point. So this is the second focal length, and we see that since the incident rays are towards the right, it's negative. First focal length will be U when V is infinity. V is infinity in the diverging case will be like this. There will be some rays coming like this, such that they will appear to converge at this point if there was no lens, but then they will refract and come out parallel. So this will be the first focal length which we see is positive. So again, first focal length U when V is infinity, second focal length, which is the more important one, is V when U is infinity, and that is the point where parallel rays meet. The first focal length is the point from where parallel rays emerge. The second focal length is the point where parallel rays actually meet. Right. Now this finishes a single lens. In the next video, we'll see a couple of other concepts, such as what happens when two lenses are separated by a distance, and of course refraction through a prism, which is also an important concept. Thank you.